Again, welcome back. I'm hoping hoping you all more or less went back to normal lives over the weekend. As I said, I was back in my house, I want to say Wednesday, or was it Thursday? One of those two. Yeah, that was different. That was something you'll be able to tell your children and even your grandchildren about. That was a once in a generation type of storm. Good. So a note on what to expect today. We're starting chapter 19 today. The way to know what's on Friday's exam is to look at the syllabus. That's not going to change from anything. The only thing about the exam that's changing is we moved it back a week. Yeah, that's right. I remember your name. I remember you did have COVID. Yeah, we did. We certainly need an F in chat for pretty much that whole week, but that's okay. So the coverage of the exam is not going to change. All that happened is we moved everything back a week. So this material will be on exam number 2, not on exam number 1. That being said, there's actually a couple of things that I'm planning even for today that that correlate well to what you'll need to know for the exam. And so, you know, it doesn't do you any harm to hear about these things. So today we're technically doing what I'd originally planned for Wednesday. On Wednesday, we'll do what we'd originally planned for Friday. And on Friday, we'll have our exam. And there'll be more information about that forthcoming in terms of how that's going to be administered. So today we're starting really a section on the reactivity of the carbonyl group. And as I believe I've mentioned, carbonyl chemistry has for decades been a major topic of organic chemistry too, certainly nationwide and probably worldwide. I would guess it's easily 2/3 of the material this term, maybe even including spectroscopy and biochemistry. So we're going back to a traditional organic chemistry type chapter, and I'm hoping to cover at the very least the first 5 sections of chapter 19. I'll mention a few words in passing that will get us through 1907 and 1914. And if we get to 1906 with preparation and formation of cyanohydrins, great. If not, we won't lose too much having to postpone that to Wednesday. And of course, I'm not taking attendance today. I will not take attendance on Wednesday either. The earliest that I will do attendance Friday is an exam. So never mind, we're not doing it Friday either, I guess. So your attendance is you're coming to take the exam. Good. So, but basically I can tell you in short now, basically on Friday, you'll just come to class as always. God willing, when the creek don't rise, the exam will appear on eCampus. You'll be able to access it. I generally give 55 minutes for the exam, and if you then need some extra time to scan or photograph it in and convert to PDF and then re-upload to eCampus. One thing I'm planning on doing a little differently from last term is that I'm going to give you unlimited submissions. So however many times it takes you to submit something that you're happy with how it looks, are we able to take the exam only during our class time? Well, the easiest thing for me would be if you came to the other class. That's after our class. But we can always work something out. Some people are taking it early also. A few of you have chosen to take it during my in-person office hours on Wednesday and Thursday, which I assume we're having lab this week. At least that's what I've heard. So that means I'll need to be there for lab supervision. And that's no problem for me. I have to be there anyway. So information on time and place for in-person office hours is in the syllabus. And speaking of syllabus, I'll have to make an updated version of the syllabus. Just the only thing I'm going to change is at the end that shows the order of subjects for each day, right? Because we need to reflect that last week mostly didn't happen due to the winter storm. Good, and you know, my my thing with putting up the lectures non-contemporaneously like this, it's not ideal. I'm not, happy about it, but it was the best solution I could come up with. So hopefully starting today, we can get back to some semblance of normalcy. Good. So basically over the next, 19, 20, 21, 22, 23, maybe, I forget if 24 is a biochem chapter or not. I think it is. So basically the next 5 or so chapters are going to focus on the carbonyl group. And your book does a little overview here, and I'm a fan of it. I think that's a good idea. So I'm just going to touch on some ideas from that. I won't go into all of the details about alpha substitution and condensation reactions like the aldol and Claisen condensations. Those we'll get to, in due time, in chapters 20, 21 through 23 mainly. But one thing, actually, I'm going to cheat and move down here because I think this almost should go before anything else. So actually, let me just edit this because we need some sort of, we need some sort of theoretical backing, and we can do that very quickly, very briefly, as to why carbonyl groups do what they do. And there's 2 explanations of what that is. And if you made your usual wild guess that they're going to be resonance in the inductive effect, well, you would be exactly right. I can tell that's not going to work. Okay, well, I'll just undo that. And here we have just a typical carbonyl group, irrespective of what exactly the functional group is. This can be any carbonyl-containing functional group. And it's true that about the following things are true about any carbonyl group. First of all, we know that oxygen is a good deal more electronegative than carbon is. So no wonder that carbon is susceptible to attack by a nucleophile. It already has a partial plus charge on it, just due to the oxygen winning the electron tug of war, right, in the bond between oxygen and carbon. And not only that, any carbonyl group, regardless of where it appears, regardless of what these other 2 groups are that the carbon's attached to, any carbonyl group has another resonance contributor that looks like this, where we put a plus charge in carbon and a minus charge in oxygen. And we go from a double bond to a single bond, and we can also redistribute the electrons this way. And that actually is also a perfectly valid way to draw a carbonyl group. Generally, we won't do that, right? It looks a little strange. And certainly the resonance form that shows no charges and the double bond as opposed to 2 charges in the single bond, certainly this resonance form here is the major contributor to the overall molecular orbital picture, no question. But this, although a minor contributor, does matter. And again, as always, I say this for my benefit as well as yours, this is not an equilibrium. This is a resonance situation. The way you know that is we haven't moved any atoms. We've only considered a different way to distribute the electrons. And so, although this is a minor contributor to the overall structure, it's one that matters quite a bit. And again, small wonder that we're going to see nucleophilic attack on that carbonyl carbon. It has a partial plus charge on it. And you can make that argument by either the inductive effect or resonance. So in chapter 19, we're going to be looking mainly at nucleophilic addition reactions to the carbonyl group. And this is just a general scheme that shows essentially what these are like. This is not exhaustive or the be-all and end-all, but in general, we can expect to have a nucleophile attacking the carbonyl carbon and breaking that carbon-oxygen pi bond. And there's several different variants on this. One thing we're really going to focus on, especially today, but certainly in future classes, is something we've said in the past as well, which is we need to be concerned with whether we're under acidic conditions or alkaline conditions. That's going to affect how we draw this mechanism. So that's very, very important. Certainly, we don't want to show any negative charges on oxygen. We don't want to have any strongly alkaline species in acidic solution. So we'll need to think differently about how we show that in acidic solution. Like I said, I'll plan on getting that even today. Once we get this intermediate, they call this the tetrahedral intermediate, right? Because that central carbon is gone from sp2 hybridization to sp3. There's basically two different things that can happen. One is we just put a proton on that oxygen, generally from either water or hydronium ion, and then we get this neutral addition product. There's another possibility whereby two protons come into the system, again, generally from water or aqueous acid. We lose a molecule of water, and we get a species of this type. This is going to be like in your enamine formation. So we'll get to that. That's a couple classes from now. And I just thought I'd show you this type of notation also. Biochemists do this a lot. And I may seem like I put down biochemists. I don't mean to. But this is kind of a nice symbolism that they use here. What they're doing here is they're trying to show that a proton comes in addition to this structure here, and you get a species like this. Over here, they're saying that two protons come in, we spit out a molecule of water, and we get this. Would the nucleophile, this nucleophile group have a charge at the end? Well, not if we're going to isolate a stable compound. So that's a good question, but remember that we always want to get to a stable neutral molecule, at least in general. Any exceptions to that are going to be vanishingly few. So it's true, though. I've not been real consistent with charges. We don't know if that's going to be neutral or of a minus charge. One could ask, would that atom then have a charge on it here? Answer is probably. So I'm being rather sloppy about all that. But I don't want you guys to focus on those details. And I know it's difficult to not focus on details. I'm just trying to give you a general overview of chapter 19. And we're going to be making references to a lot of things in chapter 17. There's a fair bit of review in this chapter as well. There's another possibility, and that comes in when our carbonyl group has a good leaving group on it. That could be a halogen or maybe OH or something. And we call those reactions nucleophilic acyl substitution reactions. And we'll get to that. That's chapter 21 stuff. But as is so often the case with the reactions like this, the main thing to notice is this process is neither SN1 nor SN2. It's a completely different critter. But in cases like this, we still have our nucleophile attacking that partially positive carbon atom and the carbonyl, breaking the carbon-oxygen pi bond. Again, give or take whether we protonate that oxygen first. Right, if we're in an acidic medium, we don't want to be making intermediates like this that are strongly alkaline. So in those cases, we would protonate the carbonyl oxygen first. Again, we'll get to that even today, and it's something we've covered already. But one way or another, this tetrahedral intermediate with our sp3 hybridized carbon atom, that's going to collapse and kick out the leaving group, and that will wind up in some inorganic side product. But our major organic product, which is again what we always want to focus on, is going to be a substitution product of this type. And there are a ton of reactions like that as well. But the thing I'm trying to say here is when we get to those tons of reactions in chapter 21 or the ton of reactions that's in chapter 19, you have a choice. You can try to memorize each separate case as being somehow unrelated to each other, or you can understand how they fall into a scheme like this and understand the pattern. And I think you know me well enough by now, you know which is going to get my vote. It's important that you learn how to recognize patterns and put things into a framework, even if that framework is not directly relevant to being a doctor. It's important that you learn how to do that because you're going to need that skill in order to be a doctor. Again, we've talked about making diagnoses. So we practice learning how to do that here in organic chemistry class. So that's an important skill, but you need to be willing to learn patterns and to categorize. It's important that you're willing to do that in order to be able to succeed in this class, as I think we've already made pretty clear last term. Good. So, so much for just the general ideas in these next several chapters. It's, I think, reasonable, since we're going to be talking about the reactivity of aldehydes and ketones mainly in this chapter, that we review, since most of this is review, how to make aldehydes and ketones. That's important. And we also review some of the reactivity of aldehydes and ketones that we already know. So that's what we're going to get to next. We already know, for instance, that you can make an aldehyde by oxidation of a primary alcohol of this type. R can be pretty much whatever you want it to be, with some mild oxidizing agent like des-martin-periodinane, or some of you are also aware of PCC, pyridinium chlorochromate. Those two reagents are interchangeable. I don't really care which you use here, but that's covered back in chapter 17. So that's one way of making aldehydes that we already know. One way that we don't yet know, not exactly, is by a selective reduction of esters. So review your functional groups if you need to. I would expect you to recognize that this is an ester. And indeed, esters can be partially reduced by an intriguing reagent called DIBAL, or diisobutyl aluminum hydride, which has this structure here. And it's a thing that's a little bit like lithium aluminum hydride, which we know the structure of that as well. But as you can imagine, with these big, bulky diisobutyl groups on the aluminum, it's a good bit less reactive. And so DIBAL will reduce an ester to the corresponding aldehyde and no further. It stops at the aldehyde level. And you also do get a molecule of this small alcohol. Almost always our R2 group is going to be methyl or ethyl. So you will also get methanol or ethanol that's that's miscible in water, so soluble in all proportions. That's going to wind up in the aqueous layer and thus in the waste jug. I did or tried to do a DIBAL reduction a long time ago. I mean, I think I tried one when I was an undergraduate, and I don't recall having a lot of success with it. But that doesn't mean the reaction's bad. But for some reason, toluene is the preferred solvent here, which is kind of unfortunate because toluene boils at like 112 Celsius. It's very difficult to get rid of. But for some reason, that's the typical solvent. And we also do need some kind of aqueous or aqueous acidic workup. You would want to put either H2O or H3O plus, doesn't matter. That's going to mainly kill off any leftover DIBAL that's left. Your book also uses the abbreviation DIBAH. I don't really care what you use. But that's another way of making aldehydes. You're not responsible for the mechanism, and it says that in the class notes. Not that it's really all that different from the mechanism with LAH, with lithium aluminum hydride. Pretty much the same idea. If you understand one, you understand the other. So that's another way of making aldehydes. What about ketones? How can we make ketones? Well, we know a few ways. Of course, if instead of a primary alcohol, we start with a secondary alcohol, again, using des-martin-periodinane or pyridinium chlorochromate, or for that matter, pretty much any other oxidizing agent you want. You can use Jones reagent, which is pretty much chromic acid, H2CrO4. Any oxidizing agent you like will convert a secondary alcohol to a ketone, and it then stops there because it's impossible to oxidize a ketone any further. So here it really doesn't matter which oxidizing agent you use. In real life, the principle I like to go by is that we use the smallest hammer we can get away with. We don't get out the sledgehammer if something smaller will work. And so if I were wanting to do an oxidation of this type in real life, I would try desmartin periodinane or PCC first, since those are milder oxidizing agents. If that didn't work, then I'd get out the big guns. But whatever your oxidizing agent might be, the ketone is the only possible oxidation product. Other reactions we already know, and really this one we also already know, that was back in chapter 17. If you've forgotten about ozonolysis of alkenes, please review that. That's another reaction by which we can make ketones. Ketones are aldehydes. And actually we learned one in this unit. The Friedel-Crafts acylation is a good way of making aromatic ketones. So that's relevant here as well. And then, of course, we also know that you can oxidize aldehydes all the way up to carboxylic acids. That was also back in chapter 17. So please review that as well when the time comes, using chromic acid or the equivalent. And indeed, if you take a primary alcohol and treat it with one of these stupidly strong oxidizing agents, that will oxidize the primary alcohol also all the way up to the carboxylic acid. It goes through the aldehyde. You make the aldehyde first, and then the aldehyde goes on to be oxidized to the carboxylic acid. But if you use a milder oxidizing agent in the primary alcohol like desmartin periodinane or pyridinium chlorochromate, that will oxidize it to the aldehyde and then stop. It oxidizes it no further because those are milder oxidizing agents. But all of that was back in chapter 17. The class notes are pretty clear in what you need to know about that. So if you need to go back and review that, I would say by all means do so. And with that, I think we're pretty good in terms of making aldehydes and ketones and some of their reactions. I still want to go over, before we get into anything completely new, I just want to refresh your memory on hydride and organometallic additions of aldehydes and ketones. That's also reviewed from earlier chapters, such as 10 and 17. Good. Any questions on any of this then? Oops, someone just bailed. I just happened to notice how it went from 82 to 81. Someone bailed on me. Oh, well. I mean, people are still sick and goodness knows what else. Okay, so let's see. And here I'm actually going into 19.7 since I think it's reasonable to do that, since that's, again, mostly review from past chapters. So what are some other reactions of aldehydes and ketones that we know? Well, we already know that aldehydes and ketones can be reduced to, let me just open up your class notes. Where's that? Yeah, on chapter 19, just so I can show you some things are already there in terms of mechanisms. Whoops. So since they're already there, I will feel free not to put them there on ChemDraw. We were through here preparing, oxidation, we did that. Good. So since we're starting in on nucleophilic addition reactions, we already know some of these. That would include hydride reagents like sodium borohydride and lithium aluminum hydride and Grignard reagents. So I just wanted to point out in terms of the mechanism of these reactions, I'm a fan of something more like this. Let's say that we treated, this would be 2-butanone with phenylmagnesium bromide and diethyl ether, followed by an aqueous or aqueous acid workup. This is a reaction we've talked about before, and it produces an alcohol, in this case, a tertiary alcohol. And by the way, the reaction of this ketone with either sodium borohydride or lithium aluminum hydride, pretty much the same. The only difference is that your nucleophile is going to be H-, the hydride ion, but pretty much the same reaction. Again, you've got addition of your nucleophile to that electrophilic carbon atom that is a partial plus charge for reasons we've already gone over. You can make the argument by either the inductive effect or resonance and you come to the same conclusion. This carbon is a partial plus charge. No wonder nucleophiles like to attack it. And you'll notice in this case, we can tell that we're in an alkaline medium. The way you know that is you look at what you're given here. I don't see any mention of anything strongly acidic. No H3O plus, nothing like that, quite the opposite. Grignard reagents, in fact, we already know are very strong bases. So is the hydride ion, so are alkylithiums. These are very strong bases. So the way you know whether you're an acidic or alkaline medium is by looking at what you're given. That's something I'm going to stress very heavily in this chapter, and I've already stressed it in the past as well. So in terms of drawing an intermediate like this with an oxyanion, we're in good shape here. We're on solid ground doing that since we're in an alkaline medium. If we were in an acidic medium, and we'll get to examples of those as well in this chapter, then we would want to think about that rather differently. So in fact, this alkoxide ion is what's going to be swimming around quite happily in our mixture until we add either H2O or dilute H3O plus. At that point, we'll use whichever one we're given to put the proton back on the oxygen, and we get an alcohol of this type. It's a very similar idea if we use a hydride reagent. And by the way, if instead of phenyl magnesium bromide, we used phenyl lithium, the mechanism's the same, essentially. The only difference is the identity of the metal cation. Now, your book shows this intermediate slightly differently. It shows the oxygen being complexed or bonded to magnesium or lithium, depending on which of those is in the reaction mixture. They're not wrong in so doing. If you really wanted to draw it that way, I have no real objection. To me, though, it's sort of like an unnecessary distraction, because if you're looking at bonds between oxygen and either lithium or magnesium, you're talking essentially completely ionic bonds. So I don't see the point of drawing them, and I generally don't. If you really want to, you may. I would accept that. I think it's fine. But I think it's also totally fine not to show them. So that's really the only point that I'm making here in your class notes. So these, again, are old reactions. We're familiar with those reactions. But we're being a little more specific about the mechanism, and I think that's all completely fine. So that being said, we've got a little over 20 minutes, and I would like to begin to get into some new material, first by covering the hydration, the addition of water to aldehydes and ketones. This reaction, I have to be honest with you, is not synthetically useful. In fact, quite the opposite. It's kind of a nuisance that we experience with aldehydes and ketones, especially aldehydes, that they're susceptible to addition of water. And so when we want to use an aldehyde or a ketone as a reagent in some other reaction, we have to take some pains to ensure that they're dry, that there's no water in there. And because generally, we don't want water hanging around. If it's a reaction that's in a protic solvent, especially if it's in water, then fine, then we don't need to worry about that. But normally, we have to take pains to keep these compounds over drying agents, like calcium chloride or magnesium sulfate, just to make sure that no water adds to them. But the reason that we're talking about hydration reactions is that they help us to, again, categorize addition reactions of aldehydes and ketones and other reactions later on as to whether they're done under acidic conditions or alkaline conditions. And so they're very useful to illustrate that. But in terms of actual synthetic use of either of these reactions, little to none. If anything, the opposite of useful. So let's say hydration of aldehydes and ketones. First of all, let's consider what happens when we're in an acidic medium. And we'll look at what to look at so that you know which is the case. Well, actually, let me do sort of a general case first. A general case would involve, let's just sort of make a generalized aldehyde or ketone over here. There you are. There's our carbonyl group. And in general, if you treat an aldehyde or ketone with either dilute aqueous acid or aqueous base of any kind, let's say water and hydroxide ion, could say you could be given sodium hydroxide, potassium hydroxide, or just OH minus, right? They're all one and the same thing. But in either case, the product is going to be the corresponding hydrate of the aldehyde or ketone, which would look a little something like this. Let me see if I can do something brilliant here. Not quite as brilliant as I'd hoped, but we'll make it work. So you'll get a species that looks like this. This is called an aldehyde or ketone hydrate, or a geminal diol. And we've given and defined both those words in past lectures. But be that as it may, you wind up with an addition product of this type. And as you see, if you add H2O to this formula effectively, you get this. So, so that's what the hydrate of an aldehyde or ketone looks like. And again, in general, this is not only something we're not so much trying to make. In general, it's something we're trying to avoid making. But this will work in both acidic medium and alkaline medium. Either of those will work. Let's do an example in acidic medium to start with. And so I'll pick a particular aldehyde or ketone. What about benzaldehyde? That's as good an example as any. So here we have benzaldehyde. And let us suppose that we treated this with dilute aqueous acid. That could also say H2O and H2SO4, you know, that you could be given that in any number of different forms. Well, again, we're used to nucleophiles attacking this carbon atom already. We've seen that happening already. But think for a moment what would happen if we did that straight away. You'd wind up with a tetrahedral intermediate. You can even go back and look at these things. That looks essentially something like this. But that doesn't make any sense in an acidic medium. Remember, we always need to show species in our mechanisms that make sense given what's going on in our medium. And since when we look at what we're given, we see we're in an acidic medium, that means we need to avoid invoking any strongly basic anions. So nothing with O minus or carbanions certainly, or a minus charge on nitrogen. No species that are strong bases. That doesn't make sense in an acidic medium, because species like that can't exist in acid. They would be immediately protonated. So that's the general idea for acidic medium. We don't want to see any strongly basic anions. The only anions that can exist in acidic medium are the conjugate bases of strong acids, Cl minus, HSO4 minus. Those are fine in acidic medium, but no alkoxides, no OH minus. Those don't make sense in an acidic medium. What about, well, that's fine. We can leave it at that. I don't want to muddy the water further. So that means that the first thing we need to do had better be protonating that oxygen. Now, how do I know what to use to protonate the oxygen? by looking at what you're given. In this case, the only thing we have around is the hydronium ion. And so that doesn't mean that you memorize that H3O plus goes here. It might not. We'll learn other reactions in acidic medium that do not have water in them. So you always need to look at what you're given. If you remember nothing else from today's class going forward, this is even helpful in your studying for the exam. You always need to look at what you're given to make sure that you don't invoke species that are nonsense for that particular mechanism. So we need to protonate this oxygen first in acidic medium. And that's very typical for reactions that are in acidic medium. So what does that give us? Well, it means that we now have, look how easy this is to do. There you go. We now have this protonated species. And in so doing, we've made this carbon atom, which is already electron-poor, which already is a partial plus charge, we've made it even more electrophilic by having this oxygen with a full plus charge on it next door. So now the only question is, what is our nucleophile? What are we going to show attacking that carbonyl? The way you know that, again, is by looking at what you're given. I'm given H3O plus, right? And remember that H3O plus always implies that water is present. Sometimes Al will write like H3O plus comma H2O. I'm not a fan. It's redundant. The hydronium ion can only exist in water. So whenever you see H3O plus, it implies that water is also present. So that is going to be our nucleophile. Again, we don't want to use a nucleophile like OH minus. That does not make sense in an acidic medium. We can't invoke any strongly alkaline species in an acidic medium. You need to know that kind of thing in order to understand this material, and a lot of material in future sections also. It's just a very important principle. Always look at what you're given and make sure that the species you draw in a mechanism makes sense. You should never make your decisions as to what you're going to put next in a mechanism based on muscle memory or rote memorization. That's not the way to approach this. You should always be thinking at every step, what should I put here? What makes sense to put here? Well, what am I given? What makes sense given what's in the reaction mixture? Good, so with that, we get our tetrahedral intermediate. Actually, I think I'll do this. So that we still have everything on screen. Now let's see. So now we have this OH group. And we also have this water molecule that we just added. Oxygen. And I'm drawing out this oxygen-hydrogen bond for reasons you'll see in just a moment. That oxygen will, of course, have a plus charge, and your tetrahedral intermediate will look like this. And now we're only just one step away from the very end. All we need to do to get to a neutral compound, remember you need to know that too. Generally, you're aiming to get to a neutral compound at the end. I'm hard pressed to think off the top of my head of any counterexamples. So that means all we need to do is pull off that proton. So how do I know what to put there to use as my base? By looking at what I'm given. All I see besides the organic species is H3O plus. That's certainly not a base. The only base that we have around in any reasonable quantity is, you guessed it, water. So that's what we're going to use. not OH minus. We need to be careful to use only species that make sense. We're an acidic medium and there is no OH minus around, at least not in any reasonable concentration. You know, you might have one OH minus around for, you know, several quintillion or even more H3O plus ions. It's any OH minus that's present in an acidic medium is in such vanishingly small amounts that it makes no sense to invoke it. Once we've done that, then we have our neutral hydrate. And hopefully, hopefully you can see the similarity between this structure over here and this one over here. They're effectively the same thing. Right, so that's how this reaction would look in acidic medium. Good, can't really think of anything else. I should mention, by the way, that all of these steps are reversible. So certainly this hydrate can lose a molecule of water also in acidic medium, and there will in fact be an equilibrium between the non-hydrated aldehyde or ketone and the hydrated one. And yes, if you wanted to find the equilibrium constant and all that stuff, you certainly could. All those things are still there. But our main focus here is this is the way we handle this type of nucleophilic addition reaction to a carbonyl in acidic medium. You need to be careful to make sure that all steps, all intermediates make sense, given the fact that we're in acidic medium. Good, can't think of anything else. Questions on any of those mechanistic steps? Well, what if we did something like this in alkaline medium? And just as I picked Benzaldehyde for no other reason than I felt like it, I'm going to pick another aldehyde or ketone just because it pops in my head. What about 2-pentanone? So there's no need to state there is excess water anymore. Yeah, I really do feel that way. Owl sometimes does that, and I'm not a fan. To me, it sounds redundant. If you have H3O plus, then it's understood that water's there. You can't have H3O plus without water. So I really wish they wouldn't do that. Good, so let's say that we're using 2-pentanone. And we haven't officially learned necessarily how to name aldehydes and ketones yet. That's part of this chapter, by the way. But I don't think anyone would be, I don't think that's gonna knock anyone's socks off with their shoes on to learn that this is called 2-pentanone. If you can name any of the other functional groups we've covered already, you know, I don't think that name will surprise anyone here. Good. So right, because it's in the second carbon, we got 5 carbons total. Totally logical name. Good. This time though, let's use an alkaline medium. So let's say we're given water and sodium hydroxide. Again, remember the sodium ion, or if we were given KOH, same thing. Those alkali metal ions are only spectator species. They don't enter into the mechanism. So since we're in an alkaline medium, let's ponder for a moment adding a nucleophile to that carbonyl carbon. In so doing, we'll wind up with an intermediate that is O minus, but now we're in alkaline medium. So now it's fine. So something I've in general noticed over the years, whenever you have reactions that will work in either acidic or alkaline medium, of which there are a few, I won't say a ton, but there are a few. One thing that I've noticed over the years is that the mechanisms of the reactions in alkaline medium are more straightforward. They're less steppy. So whereas before we needed to worry about not getting a minus charged intermediate, Now we don't have that worry any longer. Now we're in an alkaline medium. Now we can invoke strongly basic anions. Therefore, bombs away. Our nucleophile just attacks the carbonyl carbon. We break the carbon-oxygen pi bond, and we get an intermediate with a minus charge. We get, again, a tetrahedral intermediate. And that is completely fine. So over here, we've got O minus. It started out as OH. I think you could do the same thing in Al. And then when we put a minus charge on it, that hydrogen goes away. Let me be specific about my lone pairs, just to make sure I'm being clear. There we go. So you get an intermediate of this type. And in alkaline medium, everything's going to be turned on its head compared to acidic medium. In acidic medium, we said we don't want to see any strongly basic anions. In alkaline medium, we don't want to see any reactive cations. So no carbocations, no oxygens with a plus charge. Those species do not make sense in an alkaline medium. They would be immediately either deprotonated or to make a pi bond and get rid of the plus charge, or they would just suffer nucleophilic attack. The only cations that are okay to consider as being in alkaline medium are essentially metal cations. Na+, K+, Mg2+. Those are fine. Those can exist in an alkaline medium. So we get this intermediate. And again, notice when I didn't put OH minus here because I memorized it. I said, what do I have here? What can I use as a nucleophile? Well, water and OH minus are both nucleophiles, but I think OH minus is a much better nucleophile. And not only that, if we used water as our nucleophile, we'd wind up with a species that is a plus charge. And we don't want that, not in alkaline medium. In acidic medium, yes. In alkaline medium, no. So that's the type of thinking you should be doing with every species that you invoke and every mechanism you draw. It's not just memorizing what to put where and where to draw the arrows. You need to think critically about what you're invoking. Good, so once we have this intermediate, well, the only thing we need to do now is put the proton on. So how do I know what to use to put the proton on? Again, I need to look at what I'm given. All I see besides organic compounds is water and hydroxide ion. Well, I'm the sodium ion, which is just a spectator ion. So the only acidic species or the only species that's acidic at all is water. And so I have no choice. That's what I have to use. I can't just put H3O plus because I've sort of memorized that's what goes there. It sometimes does, sometimes doesn't. But there's always a good reason for it. It's not arbitrary. You always just need to be sure that you use species that make sense. So since water is the only thing around that can act as an acid, that's what we'll do. Remember, water is amphoteric. So we'll use water to put the proton on that oxygen. In so doing, we'll make a hydroxide ion. Well, we've already got those around. That's not a big deal. So that's it. So whereas I think we needed 3 steps in acidic medium, in basic medium, only 2. And as I said, that's something I've noticed over the years. I feel like reactions in alkaline medium are more straightforward. They don't require as much futzing around with intermediates, if I may put it that way. And that's it, then we're done. Those steps, of course, are also reversible in alkaline medium. And there we are at 11:30. So in fact, we didn't get to not halohydrin, cyanohydrin formation. That's going to be the first example of a new reaction. That's a nucleophilic addition to aldehydes and ketones that's actually synthetically useful. But once we understand these hydration reactions, the rest goes on like the proverbial house on fire. Once you understand what's going on with hydration in either alkaline or acidic medium, cyanohydrin formation is very easy. I'll just let you know, maybe I'll at least put the overall reaction, and we'll talk about the mechanism, of course, next time. We'll still start with an aldehyde or a ketone. This, of course, will be cyanohydrin formation. Just look at the general scheme. Of course, wait a minute, the new question. Does that mean yields tend to be higher in alkaline media than acidic media? I don't know about that. Both of these are reversible processes. I think instead, whether we use an alkaline medium or an acidic medium more depends on the nature of the reagents. But we're going to see that there's some reactions that happen in acidic medium only, and some in alkaline medium only. And I think if you guys keep an open mind, you'll see at those times there's good reasons for that. So the acidic version of the reaction, it basically uses HCN and typically aqueous medium. Or you can do this under alkaline conditions as well, using either sodium cyanide or potassium cyanide. Either way is fine. And the reaction looks very much the same, except instead of two OHs, you'll have one OH. Of course, that oxygen in the OH used to be the carbonyl oxygen, and on the other side, a nitrile functional group. Which, by the way, don't forget the structure of the nitrile group, C triple bond N, right? That's an sp hybridized carbon. And both of those will work. But we'll leave those mechanisms till next time. And this now is actually a useful reaction, because once you have that nitrile group there, there's things you can do to that. You could reduce it to CH2NH2 with LAH. You could hydrolyze that and make a carboxylic acid. So now we have options. This is a much more synthetically useful reaction, but I am out of time. I need to let you guys go. So have a good day, stay safe. I guess I'll see you all on Wednesday.